persons. Yeah, here you go. To Adam, Gary, Boris, or Janji. He goes as Beckett also. And these are the emails of these people. Any questions so far? No? Okay. Our first presenter, you can come up here and set up. Here's the mic. Here's the mic. Give me a second. Okay. So Harshit, our first presenter, he's a software engineer on data movement engines team at Netflix. He's the lead for schema platform and data platform and works on Apache Kafka at Netflix. He's building up and operating the fleet of Kafka clusters and associated libraries. He's also worked on real-time data processing platforms like Apache Flink and Mantis before that. Previously, he worked at Uber, where he spent his time building an exception logging platform for mobile and backend services. Outside of work, he's a proud father of a 4-year-old who he loves biking with. That's great. He also loves to travel and hike around the San Francisco Bay Area, though the latter is difficult these past few years. Welcome.
My presentation because you're sharing. Thank you. So thank you for the kind words, Boris. It covers the about me as well that I'll do again, hopefully with a joke. Yeah, hey everybody, good evening. I'm here to talk about how we are at Netflix scaling Kafka for the big blockbuster live events that we have in the past and that we are going to see more of for Netflix. Thank you for attending this talk. I really appreciate it. With that, let's get started. A little bit about me. So I'm a software engineer on the Kafka schema team at Netflix. I was previously at Uber, like Boris mentioned. I'm a proud dad to a 4-year-old. He's a big car person, so I apologize in advance for some of the car memes or pictures that I'm using in the slides. I love to travel. I love to bike. Hiking dropped from here. I don't know what happened in the last few months, but yeah. And I love to watch Netflix, of course. And I'm into Formula One. So that's a little bit about me. This is a rough agenda of what I'm going to be talking about. I'm going to give you an overview of what live events are in the context of engineering, like how does it translate to? What are the challenges that teams across Netflix face, but more specifically, the challenges that the Kafka team face. And then we're going to drill down into one specific area and talk about that. That is solved by Kafka Cruise Control and some modifications that we made to it that LinkedIn graciously accepted into the open source. Then we'll go talk about the solution, some of the examples that it fixed, and then the future work that's still left on my team. So with that, let's get started. But first, I want to quickly highlight this chart. This is a daily trend of Netflix viewership. Of course, this is not actual data. I would get sued by Netflix if I show the actual data right now for the week, but the trend is similar. So you would notice that over the weekends, the troughs go up higher. That means weekend traffic usually is more than weekday traffic, which makes sense. People have a little more free time. The peaks, they don't show as much of a big trend because evening viewership is pretty consistent, weekday or weekend. This is without the live events. So if you don't include any live events, this is what happens. That changed in 2023 when Netflix started doing a lot of big live events, starting with Chris Rock. I don't know, hands up if anybody watched that live or later the recording. Okay. Oh, a few. I was not expecting that. That's good. In November of last year, however, Netflix had one of the biggest boxing matches in history. I mean, it's only it's only smaller than the iconic fight between Ali and Foreman. I was not around to see that. I was too young, not even born. This particular fight had about 108 million plus live viewers and 65 million concurrent viewers at the time. This was followed by two of the most streamed NFL games ever with 30 million plus live viewers and 24 million concurrent viewers. We also like to push boundaries. So we said, okay, let's add ads into the mix. And this was the first live streamed event that had ads for Netflix. Netflix was just getting started. The mandate that we as Kafka team got was we are going to do these big routine live events in a routine fashion, and we are going to do them in a bigger and bolder fashion for 2025. So like maybe 5, 6, something like that. I don't know, some number, but yeah. Now let's go back to the graph again. So what happens when a live event is actually happening? You see that there is especially a big one. It's a planned increase in traffic for a very small duration, like the duration of like maybe 3 hours or 4 hours, whatever the duration of the live event is. And the traffic goes up really quickly if it's a big one, like the boxing match or something that I talked about. So the scale has gone up about 2x in traffic. Now I want to emphasize on this planned increase. So planned, it means that you have time to pre-scale, but you don't have any time to react. Like if you think that your reactive order scaling is going to work, it's going to be too late. Your cluster is probably going to be underwater by that time. Short, because the capacity increase is not permanent. It's not like you are expecting that traffic overall for the remainder of the year or the quarter. Well, how do you deal with that? Usual solutions, let's do order scaling. But scaling stateful systems, especially like Kafka clusters, is hard. Doing it at Netflix scale is probably harder. I mean, I see a lot of folks from LinkedIn here. I know from experience and probably their conversations that they find it extremely hard as well. Let's talk a little bit about the scale at which Netflix operates. It's present in about 190 countries. There's about 300 million subscribers today, with about 1 billion devices that are being used to watch Netflix around the world. In Kafka terms, that translates to about 150 gigabit per second data. This is a bit old, but yeah, about 8 petabytes of state that's being persisted on Kafka cluster brokers, and about 480 clusters or so across 10,000 brokers. Well, how do you prep for such a big event then with that scale? Two obvious answers. You do horizontal scaling and you do vertical scaling. Horizontal is add more instances, and vertical is like you change the instance type. That's exactly what we do for any kind of pre-scaling. So for horizontal, we add Kafka brokers, we add partitions to topics, whatnot. I hope everybody here is familiar with topic and concept of partitions. So I chose to ignore that detail. And then for vertical scaling, that means changing the instance profile to say, hey, you want to go from 2 CPUs to 4 CPUs or 8 CPUs. You want to 3x the storage, something like that, based on the anticipated load that the live event is going to put. I like vertical scaling because once you do it, you can reclaim the stage, scale back. So you can go down again once the event is over. Horizontal scaling is a little more permanent. So you need both the approaches to deal with this. And in fact, one of my colleagues spent time to really make the vertical scaling faster as well, so that you can scale up and scale down a Kafka cluster in a matter of few days, as opposed to weeks that it used to take. For the horizontal scaling especially, we use cruise control. So whenever we use like scale, we have to run the cruise control to do the Kafka rebalance so that the partitions are correctly aligned and whatnot. And that's going to be the main focus of my talk today. But before, of course, there's so much context. I hope I'm not boring you with the details. But what is cruise control? It's a LinkedIn open source tool that simplifies Kafka operations. I like to think of it in 3 high-level terms. The first is cluster management. It is responsible for balancing workloads, partition optimization, so that they can be placed in a fair and equitable manner. And it also triggers the rebalances. So if you trigger a rebalance, it acts as the brain for how the rebalance is going to go. The second thing is a self-healing mode, which detects and auto-remediates any kind of imbalances that you might see in a cluster. We have this off by default at Netflix because we want to run a little more control over, exercise a little more control over how the cluster behaves. And the third thing, which I really like, is that it prioritizes production traffic. That means any produce or consume messages that's happening via your users get priority over any rebalancing data needs that Kafka has. I think this is probably, I look at Alan eyeing me, so I don't know, maybe I'm misspeaking, but yeah. Here's a quick snapshot of how the UI looks. If you have not seen the cruise control UI, it's basically like there's a lot of options at the top. You can view those tabs. You can take actions like let's add brokers, let's remove them. In a case of emergency, you can demote brokers as well. And then 3 unhighlighted ones, which say, hey, you can trigger a leader election or rebalance the cluster and whatnot. So we use generally these operations pretty well as need arises. This is an interesting view that we found in the recent version of Cruise Control UI, which shows you the breakdown of each topic partition spread across the brokers in the cluster. And I'll come back to this graph later in the talk, but this was a very key insight that was relevant to the problem. Now, how does Cruise Control do this? It has a list of goals split into 2 categories: hard goals, which are invariants in the system, the constraints that cannot be violated. Those are also shown in bold letters on the right, in the image on the right. And then there are soft goals, which are nice to have. You can break those constraints, but you ideally want to satisfy them as much as possible. Some of the examples of hard goals are you want to be rack aware. So you want to make sure that the data is distributed across multiple racks. You want to make sure that network is evenly distributed, something like that. And then the soft goals are things like, hey, we want the replicas to be balanced across the cluster. So a broker 1 should have, say, the same number of replicas as the other broker. This is something that you get for free from the open source. What it does with the goals is once you configure the list of goals that are suitable for your cluster, it iterates through each of the goals in the priority that was shown. So it runs a for loop effectively, which says, let's iterate over each goal, initialize the state. For each broker, let's try to see if the broker is balanced. And if it is not, then figure out a way to balance it and then move on to the next broker. And keep doing this until you run into either a constraint violation for hard goal, or for a soft goal, you can just bail, and at the end of it, you can say the cluster is balanced now. So why am I telling you all of this? Well, coming back to this, we do a lot of pre-scaling, especially horizontal scaling, and then we want to run cruise control after that. So let's take a scenario, like you're adding brokers. You say, okay, you went from 2 brokers, which had 2 topics, two topics and 2 topic partitions per topic. And the dashed ones are the followers. And then you add a new broker to it, like broker 2. In the next one, I've removed the replicas, the follower replicas, because they get too noisy in the image. But what you want to do is run the cruise control rebalance algorithm, and then maybe it says that, okay, let's ship 2 topic partitions to the new broker in some scenario because it matches up the configuration. Let's take an example of adding partitions as well. So you add 1 extra partition for each of those topics. And when your cluster controller decides to place topic partitions, it could place them arbitrarily, like place them all on broker 2 or place them some on broker 0 or broker 2, whatever it is. And then you run cruise control on top of it. It comes up with this balanced view and says, okay, now broker, each of them have 2 topic leaders per across. Looks good enough. You're like, okay, we are ready for the live event. Let's watch. I, as an on-call, would be like, let me get my popcorn, sit, watch the boxing match, and go from there. But oh, I get a page right away. I don't know what's happening. Let's look at the metrics. I see that the request handle idle %, which says how much idle capacity is a node has. You notice that there is some variance. Like the green is very heavily loaded, the blue one not so much. Very idle. Let's see what's going on. Again, made up numbers for illustration, but yeah. You look at the messages in, you notice that the red topic is getting far more traffic than the blue topic. You look at this view again, the view that I showed from before, the problem becomes obvious. Broker 2 has 2 topic leaders, and while broker 0 has none of them. So that's why broker 0 was so free, whereas broker 2 was so much under load. So what do we learn about cruise control from this? One of the insights is that it optimizes a balanced workload for normal traffic. Like if there are no abnormal events like backfills or live events, then the state and the growth is in a linear fashion, then you would get like an optimized placement for that. It only looks at the broker system metrics like CPU, disk, network, and you get like the consumer and not the producer view. So they could suffer, they could see data skew or whatnot, and just like we saw here. Well, how do we fix it? So you remember that graph that I showed you? Well, what if we try to balance that graph for each topic individually? And that's effectively what I'm talking about. Like, let's take each topic and rebalance the topic partitions within it in isolation. We came up with a new goal called topic leader replica distribution. And we say, okay, now for each broker in the loop that I talked about earlier, let's try to run it for every topic and say, let's balance it out for across the broker. So yeah, this is the goal for each broker. You run through each topic and you say, okay, now let's make sure that the broker has an average number of partitions. So how does it work in practice? Well, you look at the average number of leaders. So for the blue one, you get one topic partition per broker. And for the red, the average is also one. And you notice that for B0, blue had two topic leaders, so 0 and 2. So you decide to send one of them to the one that's up to the broker that's available, which in this case happens to be broker 2. Then in the next control loop, you identify that broker 2 has an extra partition of red topic. So you send it to broker 0's way. And then you end up with this picture where everything is one per topic. With me so far? Okay. Some other implementation notes as we did this is the soft, you still end up with these followers that are lopsided in case the red on broker 0 has still a lot of overweight compared to the blue on broker 2. And to fix that, we use the soft goal that cruise control already has called topic replica distribution goal, because it's a best effort thing. The follower does not add a lot of system resources utilization on the broker, so we are good. And of course, we want to run this with the rack-aware distribution goal to make sure that the data is spread across the racks that we have. So we wrote the code, looks good. Let's try it on the simulator. The first thing I did was set up a test cluster, a unit test. So it's again a unit, so it's all a unit test for now, but I set up a test cluster with 6 nodes, and each node had 2x the number of topic partitions on it. So you see that blue increasingly linear line if you look at the broker and the topic partition count on each. And what happens after you run this goal is that you get a flat line at 10, which means that the strategy kind of works. The yellow line shows the follower replicas, and you would see that it's not balanced. It does an okay job, but not fully balanced. We break it down by each topic. So you have 2 topics on the system, T0 and T1. You see that what was a line, like a increasingly growing line with a slope of 1 becomes a flat line, which is what you want. So you have a reasonably high confidence that this is going to work. We also ran a simulation on production cluster, a unit testing cluster modeled after production. So we said, let's get the placement from production, run it against a unit test to see how well this goal is doing. And that was like a very effective strategy to see how are the tweaks that are needed to be made to the goal and just validate unit tests. Again, you see that what was a big band between 400 to somewhere around 800 becomes a flat line at around 500. There's still some unevenness. Some things might be at 499, some things might be at 501, but by and large, it's about pretty accurate. The yellow band is, however, much wider now. It went from 1,000 to 1,600, but now it's going from 1,200 to like 1,800 or so. And that's just because we didn't care enough about replicas at that point. Now, okay, the results look promising. Let's try it on a few production clusters and see how the rebalance is actually doing in practice. And the results are very similar. Remember this graph that I showed you from the beginning? For these 2 topics, well, there are more topics on this cluster, but just for these 2 topics, it looks something like this after the rebalance is executed. I showed this to one of my engineers on the team, and he was like, this graph is too good to be true. Like, you are probably doing something wrong here. So double check, triple check. And that's what we did before shipping it out. And we noticed one of the things. Oh, I'll talk about that. But let's take a look at the leader count distribution as well from before and after. So what was a wide band somewhere between 4,000 and 6,000 is now narrowed down to a value around, I guess it's around 5,000. Yeah, something around that. And in between the zigzag is when cruise control is trying to move the partitions around to satisfy the constraint. Overall, so strategy works very well. We also had some good side effects because of it. The first one was there are these other scenarios, except for live events, when people are running like backfills or restatements, and you notice that some brokers are extremely overloaded compared to the other ones. This strategy helps avoid those outlier broker scenarios as well. Our users have noticed the balance. They have noticed a far smoother, tighter band around bytes in and bytes out, which actually keeps their apps stable, like makes their auto scaling jobs easier and whatnot. It also leads to resilient operations overall for the Kafka team. Some of the future work that's still pending is we have to handle off by one errors. So what happens is if you have topic partitions that are not a multiple of the broker count, you end up with these some brokers which have one extra partition on them. And ideally, you would want to increase the partition count to match the broker value so that the remainder is zero. It's tricky because you have systems like Flink or other Kafka apps which might not be listening to partition changes notifications and would say, hey, they will just forget reading about the new data. So partition expansion is a tricky thing that we need to coordinate with one other team, and that's why it's not rolled out. The second thing we want to do is right now it's a human in the loop process. So every time somebody horizontally scales, they go and press a button to say, let's rebalance the cluster with these settings, and we want to automate it. Because A, it helps with automating horizontal scaling end to end. B, sometimes the cruise control node dies and you have to restart it, re-trigger the rebalance, and do all of those things. This would just take away the guesswork out of it and say, okay, now you are at, once you trigger this workflow, you're at peace and you're good to go. I probably brushed through it very quickly. Time for some questions and then.
So I assume your production clusters are supporting lots of topics with lots of partitions to the topics. So the odds of an mod zero division of those topics and partitions across the cluster is fairly low, right? So it's not like you've got 35 topics, each with 35 topics, each with 10 partitions per topic. So 350 divided by your nice 35 broker cluster, right? It doesn't divide that evenly. What other things did you see to try to help balance that set of leaders across things as you did that? Because I mean, most topics aren't going to be the same number of partitions either. You're going to have some topics will have 13 partitions and some topics will have 97 and all these other constraints.
Yeah, that's a great question. So I look at it at two parts. The first part is, hey, how do you make sure that the off by one error is not repeated on the same broker over and over again? And we actually did a secondary check in the algorithm that I showed you, where we are sending a replica and bringing a replica back to say, if let's also look at the total number of leaders that are present on this broker and pick the one which has lowest number of leaders so far. So that way, that ensures that you get some fairness across the brokers on leader distribution. But yeah, that's a great question. The second is, it's just a reality of the situation that you get too many topics with two different topic partition sizes. That's not equal to the broker. And at that point, you end up with these off by one errors that you have to address. We think that adding more partitions at that point and allowing the downstream and the upstream to be aware of those added partitions so that they can safely consume data is an effective way to solve the problem. But we are not there yet. There was one question in the back, and then
I wanted to know was Are Kafka clusters at Netflix using Zookeeper or Graft?
Yeah, right now they are using Zookeeper still. Yeah,
Any more questions?
it's like
So what are the adjustments that you need to do after the live events is over?
yeah, again, a great question. So for vertically scaled clusters, we change the types again to bring them down. For horizontally scaled clusters, we don't have that luxury because then you have to uh, safely remove the brokers by demoting them, moving the partitions away and doing those things like that. But we haven't gotten that workflow right to be able to do that. So for horizontally scaled clusters, we leave them as is for now. So that's where the human judgment in some ways come in place, where we try to say, hey, does it make sense to scale this cluster horizontally? Yeah, and we try to do it less often. Yeah. Sorry for putting you on the spot, Alan, by the way.
Sorry. Thanks for the presentation, and I'm glad to see the skill has grown a lot since a few years ago when I was at Netflix. But I'm curious. So so right now you have 475 clusters. Do you think it's a scalable solution to keep adding more and more clusters? Does that add a lot of operational overhead to manage so many Kafka clusters? And then my second question would be, do you leverage, since you have so many Kafka clusters, is there any kind of abstraction or virtualization where you leverage clients, like you build some kind of abstraction on the client side where maybe one topic can span across different clusters in order to better scale? Do you have something like that?
Yeah, those are very interesting questions that we have just only started thinking about. I think more than the scale of the cluster, the scale of the Kafka fleet, the interesting questions are the access patterns for Kafka have been changing or evolving over time. Like, for example, the requirements for live events was very different from a year or 2 years ago. And that meant that you had to be more resilient on operations, and that led to work like this. So yeah, long story short, it works so far. We think that it's going to work for some more time. We don't know where the breaking point would be, to be honest. And as per the second question, we have a different abstraction where we don't split the data for a single topic into multiple places. We sometimes tell users that, hey, do this on your own and maybe figure out a way to reconcile. There is a separate abstraction which allows you to move data from point A to point B. It used to be called Keystone, now it's Data Mesh. There are some amazing technical blog posts from Netflix on that, which allow you to see the problem from a different lens, which is like, hey, if the data on a particular cluster is getting too big, then you have the ability to move the topic itself to a different cluster in a managed way. There are limitations though. So yeah, that's the long and the short answer here.
Hey, thank you for the presentation. A quick question. Since you have like hundreds of these clusters, actually my question is about the multi-tenancy. For example, I suppose your service or clusters is used by cross-company by variety of teams. Are these each cluster dedicated to one single team used, or do you share, like how do you manage this so many different teams to use your resource, let's say cluster topics?
Yeah, that's a great question. So we have a mix. We have some clusters, like especially in the abstraction, where the abstraction is managed by a central team, which says any team can write data, and then they take care of making sure that the cluster is right-sized for the scale that you are going to put at it. There have been some very few instances where this kind of bleeds into or is exposed to other teams, but otherwise we have multiple clusters per like a group or group of people, and that could be a logical group or a team or a organization. I like to think of multi-tenancy not in the sense of, hey, who are the users, but in terms of what types of applications are you reaching out to it. Like, are they important services that would break the business if they're down, or are they like for testing only? And we have mixed usage even there. Yeah.
All right. Any questions online?
Yes.
Radhir is asking. Oh, go ahead.
Yeah, Boris, we have one question. Randir is asking, does this take care of Kafka-less? So I believe he's referring to the use of cruise control and its impact on the lags observed on Kafka.
In my experience, operating cruise control this way does not take away the bandwidth from production. Like the rebalancing flow is, I haven't looked into the details too deeply, so somebody here might be more knowledgeable, but the way I think it works is the follower replica is moved first before the ownership or leadership is granted to that replica. So I haven't seen any impact on lag whenever we are doing these operations. But yeah.
Okay.
Yeah.
Harshit, thank you very much.
Thank you all.
It was a great presentation. You can stop sharing. Let me share. I'll take the computer there. Let me introduce you. Okay, our next presenter is Talat from Google. Talat is a senior software engineer at Google and an Apache member. He's an active contributor to open source projects such as Apache Iceberg and Apache Beam, and is passionate about building scalable data processing system. Prior to Google, Talat worked on the Cortex Data Lake team at Palo Alto Networks, where he helped secure customers by developing a streaming data platform leveraging Apache Kafka, Apache Beam, and Apache Flink. Please take it away.
Can you hear me? Yes, nice. Today I will try to explain the I believe this is a new streaming model. As you know, my previous presenter, our previous presenter is explained that the Kafka related challenges, and hopefully we can get rid of that with this presentation. Here. Okay, sorry, this is not my machine. That's why I have one challenge. I lost the screen. Here. I found it. Here, I believe I don't need this. Okay. Yeah. Okay.
You good?
Yeah, I'm good now. But it's smaller.
Give me a second.
That one.
No, that's different. It's not much better, but better.
Okay. Up again. I'm just trying to get my notes. That's why. Sorry for guys. The somehow the screen is not cooperating with me. Okay. Should I change? Okay, here. I will change here. Oh, come on. Does it? Now I am able to see that here, right? Everything is works now.
Yeah.
Okay. Okay, today I will try to explain, I don't know the audience, the background. That's why I slightly explain about what is Kafka, Beam, and Iceberg, and what is the motivation about this talk, and also the how streaming the as a solution, how the Beam streaming is working with that. Let's start. For I believe, do you know the Kafka, right? Okay. Basically, we are at least I am very thankful for the LinkedIn to to make the open source for Kafka, and everything is changed after the making the open source. Till that time, we have to use Hadoop, then to start streaming processing. And the Beam is our project. Basically, try to solve that multi-runner issue. When you write a code with the Beam, you can easily run all of the runners, as you can see that Dataflow, Flink, Spark, and others like Apex, IBM Streams, or Samza is the one of them. Based on my the public knowledge, LinkedIn also used the Beam in their streaming processing. Okay. And also, in addition to runner side, you can also write your code in the whatever the language you prefer, like Java, Python, Go, and or SQL. Independent from your language, it can run the runners. Like most of the data stream processing engines or data processing engines are written in the Java or Scala, but Beam is allow you to write the code with Go or the Python or any other language. Do you know Iceberg? Or do you use Iceberg in daily basis? Okay, nice. The Iceberg is open table format. When I heard this, the term, it didn't make sense anything else for me. But basically, we can say that Iceberg is a kind of a sophisticated metadata layer on top of the raw data, which defines some kind of specs to write the data in addition to your actual data. And it maintains versions and the structure of the table. Okay, program definition. I multiple times heard from the Netflix the presentation about their streaming events, and usually when you look at the streaming pipelines, you have a raw data, then a streaming engine like Beam just do the ETL, write back the Kafka, again to do some filtering, extraction, or Kafka doesn't have that capabilities like the filter in the broker side. That's why you rely on some streaming engine, and eventually you can store that pipelines on a storage. But Kafka is not good for everything, right? I don't know, what is your day-to-day job you are doing that, but at least in my previous experience, we don't use the Kafka for all of the steps. Usually we use some near real-time required steps with the Kafka, but other side we are using a storage system, like blob storage or those kind of things. And this also, since day one, the Beam is also, the advocate about the unified data processing. Basically, data processing is a spectrum. If you go to right-hand side, it's more real time, and if you go to left-hand side, it is offline. Yes, Kafka definitely is good streaming engine, and you can use as a storage for your real-time workload. But there is also, the untold Kafka issues. The people usually don't mention that, or maybe they mention in the meetups like how they find the solution for those issues. such as operational overhead. You have to run whole team to manage the Kafka and to keep it live and reliable. And this also brings a cost because you have to use the servers, multiple machines to process the data. As previously I mentioned that Kafka is kind of raw data. You cannot do filtering and do anything else on site on the Kafka brokers. You have to deploy some streaming jobs additional to do that. And also parallelism. The Netflix is all, at least with cruise control, all about the unbalanced broker issues, but still there is a rigid parallelism, as the previous talk mentioned that the filling or other runners, they may or may not detect new partitions, and your job may lose the data about that. These are mostly, so far I saw, these kind of issues on my, the previous experience. And, why this talk is, I decided to present, actually, when I think about the Kafka system, basically I feel like, the right path and the behavior of the data, like you have a producer, you commit your data to Kafka until Kafka is, make that data is, the reliable, it will not send back the ACK. And whenever the data is secure, it just sent back the ACK to producer side and producer know that. And last couple years, I start working on the Iceberg open source project, and I was looking at how it's doing their rights. I just want to go a little bit dive because Iceberg is pretty new compared with the Kafka or Beam. I don't want to go the details about those, but for Iceberg rights specific, basically there's a 3-step. The first step is that your writer is write your data on the blob storage or your file system or wherever you want to store the data. Then the writer is prepare as some snapshot, which is a metadata layer. It creates some metadata information as a second step. Then it just commit the catalog. For the write data and delete data files generation, you can create anything else like Parquet, ORC, or Avro. It's up to you. And when you write your data inside of the Iceberg table location, basically it is a blob storage bucket or folder. It is invisible to readers. It's very similar like if you don't commit your Kafka rights, it's not visible for the consumers. And when the Iceberg writer is start preparing the metadata files, actually it is a kind of a tree structure. And for that tree structure, it creates the manifest files, which represent multiple data files and some information about the data files. And then it creates the manifest list, which is basically a list of the manifest files path and the snapshot. Snapshot is themselves is not the files. Actually, it's stored in the JSON file. They call that metadata JSON. And still, data is not available for the readers. When we do the commit, it's like Kafka commit, basically you get a snapshot ID. And snapshot ID is very similar, at least it seems to be similar for me, as an offset, for your message. And for Kafka usage, that, you can write a single message also too, like per message per website, or you can write a batch of the messages in the one offset, and on the reader side, you can also decompress that messages. In this context, you can think like, the per snapshot, you have bunch of messages rather than a single message. And that bunch of messages is represented as a snapshot. Whenever we do the commits, and it's available for the readers. And also snapshot itself is increasing and in order, and it's like similar with the offset. Is it so far clear for everybody? No? Okay, I start thinking that, what if we start using the Iceberg rather than the Kafka? because as we mentioned that, in our previous slide, data processing is the spectrum. We may require a less latency, which is near real time. Kafka is awesome for that, and Kafka can provide a sub-second latency, but not all of the data processing pipelines require the sub-second latency. If your pipeline is level of the minute latency, and maybe Iceberg can work for your pipeline. And for our previous pipeline, we just replaced with the Iceberg, the Kafka with the Iceberg in the middle. Initial Kafka pipeline is still raw data, which receive the data from the devices or different systems, which requires the less latency. But after the ETL pipeline can write the data on Iceberg, and the rest of the pipelines also can continue with the Iceberg. With that, let's look at the writing part. This is Iceberg sync that you can define inside of the Apache Beam. Basically, you just specify your table. If you want to drop some of the columns you are not interested in, you can drop it, and you can define your partitions, and that's all. And also, this is kind of unique for our implementation. If you want to create a dynamic topics based on some values you receive on the event, you can specify the table on the table name. You can specify the columns, like in this example that I defined. It will create a dynamic tables for Iceberg. Creating the topic in Kafka is kind of expensive operation. Like it's not that expensive for creation, but the rest of the life cycle is expensive. But creating a new table on a blob storage, it's not expensive operation. It's just yet another folder under your bucket, and you can dynamically do that. This helps us to currently when you write your Kafka, all of the consumers has to read that topics data, no matter what. And the downstreams, they are just do the read amplification rather than write amplification. We have single writes, but same data we keep reading multiple times. This also become a costly about interzone communications, because basically you have to stream the whole data to between the zones. And also it makes CPU processing is higher, because you have to process the same data no matter what. If you are looking at single element, you have to still process all of the data and find your single element. In this source side, let me go back to in this presentation. As you can see that this is my sync, but for feature extraction job, this is actually a source like Kafka. And on the source side, it's also there is a beauty. You can dump all of the data a single Iceberg table, directly reading from Kafka and writing the Iceberg. When you want to read it, you can do the filter pushdown. Filter pushdown means that you don't need to read the data itself and just read a specific columns without reading the whole data. This is also another, I don't know what you can say, that maybe cost reduction or performance improvement, they are going hand to hand. And you can say your table, as you can see, we create the dynamic table in here. We say that flights, airlines from origin. Now I'm able to directly say, hey, this is American Airlines and JFK source flights. And I just want to keep plane model and duration. I don't care about the other fields, and filter the destination is MAD. And in here, I'm also defining that how frequently I want to check my source. And basically, this is a kind of pull model. You keep looking every 5 seconds. You just look at that. And also, we have a offset strategy, like what the Kafka has that. earliest offset, latest offset. You can read from a specific snapshot, which is offset directly if you want to do backfill. And the rest of the pipeline is just this. How it is working, it is very similar to working with like Kafka. We are just keeping when you say the earliest offset, of course, your snapshot is the 0. And based on the interval, let's say that in this example, we say 5 seconds. We are just waiting 5 seconds and read whatever the snapshot is available. For your each commit on the Iceberg side, it's just translate as a snapshot. If you do the 4 commit, basically you will have the 4 snapshot. And we just, every 5 seconds, we just keep reading the data and start processing your data. And another one. And it's over the time, it will go continue like that. And also reverse is possible, like, rather than reading the earliest, you can say the latest, then we can start middle of the snapshot, whatever the latest snapshot it is, and we only look to whatever append after that. Okay, these are the internals, how we implemented this Beam Iceberg source. Basically, we are, as I described, that each snapshot has a data files, and the data files may have the different size of the files. And in here, we are just using the incremental append scan, which is provided by the Iceberg. And we are just saying that, our target read split is the 32 megabyte. And these kind of informations also we define for the Kafka consumers. Normally it's coming by default. This is also default too, but you can tune it like, I want to read 100 megabytes or 10 megabytes, 5 megabytes. It's totally up to you. And the Iceberg planner is just create a combined scan task, which is just only metadata. And it just calculate based on the manifest metadata, how much file size are, what is the file size and what has to be combined scan task. And in this example, you can see that there's a 4 megabyte file, 8 megabyte, and 20 megabyte just come together as a combined task for this snapshot, and so on. And all of the combined tasks, these are metadata informations, and the path of the files just reshuffle across the workers. These give us some auto-scaling capabilities. In previous slide, they mentioned about that, when they have the live event, they cannot do they cannot do the horizontal auto-scaling, right? And this is kind of independent from your throughput, because basically your workers are plan ahead to process your data and use all of the workers and utilize all of the workers. Then after the shuffle of the workers, each worker will have their own reader, and the combined task will read as a sequentially. And in this context, you can think like it's round robin writes on the Kafka, and for that round robin writes, all of them will read as a sequentially. Let's say that this is also a common program issue with the Kafka. Somehow, one of the partition on the topic is just backload because that consumer is not fast enough, and there is no way to share that work between the workers. If that consumer is not fast enough, and you have a backlog on the specific partition. For our Beam source, we have a splittable do-found functionality. If we detect any of the workers are struggling about processing the data, it can split and assign the work to another worker. We don't read the data. That's why this is the easiest way. Just send the metadata to other workers and get help if they are done. Key benefits of this approach is basically we simplify the operations. We leverage the Google Clouds or any cloud, sorry for that, any cloud's blob storage. without maintaining we don't need to maintain the reliability kind of things on the data layer. And it's a unified storage, like you can use the exact same table for different needs. If one consumer wants to just get the source of the flights, another consumer wants to get whole data, you can share the same bucket between the different consumers. And also massive cost saving, like the cloud storage of course is cheaper than the maintaining the VMs or the SSDs, EBS, those kind of things. And also there is no cross network transfer, data transfer. Even there is a cross network data transfer if you choose your cloud storage as a single region. The data transfer is less than the Kafka in this context. You may say that, hey, I put my Kafka in the same region and same zone, and my consumers are exact same zone. There is no any network cost. Yes, you are right. But at the same time, in this context, you don't need to transfer that much data also too. And efficient processing, we haven't published the benchmark. Hopefully, end of the next quarter we will publish the benchmark. But initially testing, what we saw that it is the way higher processing and utilization compared with the Kafka source. The Iceberg source is more efficient, less resource required for the processing the exact same data. And of course, flexible and efficient auto scaling is another benefit. Maybe you are dealing with the streaming aggregation and those things. Currently, our system is, unfortunately, it's supporting the processing time rather than the event time. But the next quarter, hopefully, we will make also event time is available. And for us, processing time means that snapshot itself, when the snapshot is created, and when we start supporting the event time, it will generate the watermark assessment based on the event. And you can use your input like arbitrarily snapshots. Think about every 1 hour you create one snapshot. Normally it's too long, to be honest, but this was the drawing I had. And you can align the event windows based on your watermark strategy. Okay, what is next? Whatever I explain, everything is open source, and we are working on the full CDC write and read, batch compaction, and continuous streaming compaction. Currently, you have to define your size of the streaming, how frequently you want to create your snapshot. But hopefully, going forward, we will have a continuous streaming compaction. You don't need to think about how frequently you need to create a snapshot. You can create snapshot as much as possible. And you can eliminate the small file issue using the continuous streaming compaction. And maintenance task like compaction, of course, and event time, as I mentioned. Questions?
Thanks for the presentation. It was very interesting. My question is, when you replaced Iceberg with Kafka, if your Beam ETL job has gone down because you're doing this 5-second polling, with Kafka, you've got queued messages. With Iceberg, how do you go back and pick up the jobs that didn't get finished because, let's say, this system was down? Do you have a mechanism for that?
Yeah, Iceberg job is actually, it's not different than the stateful streaming job. And basically, we keep the snapshot ID for what is the latest, like the latest offset. And we commit our snapshot ID on our state backend. And basically, if you are doing a streaming aggregation, you should have a state backend, and you have to have a reliable state backend. The only differences is that we just need to keep very small information. We are not keeping the files or metadata files, just snapshot ID, which is a string, And it's, I don't know the exact string size, but it's very small. No, the limitation is that we are processing per snapshot, and we are acting snapshot like offset, Kafka offset. You cannot process, the partial offset, right? I see. Sorry for that. Yeah, I understood. Now what you are asking that here, right? This one, this one. Which one you mean that? This is, and this information is that yes, we are. I can say in the first place that the processing is triggered by the per snapshot, but while we are processing to leverage all of the workers, yes, we can process the half of the file in one place, half of the file another worker. Yes, whenever it's done, we commit all of them in the one shot. And that's why I describe in here, I also, to make emphasize in here, like, deliberately explain the right path. The right path is that Iceberg is not, if you write any file and that files are not, the complete, they are not available. The first you write the data files and you assume that data files is done, then you create manifest, then you commit the offset. In these three steps, if one of them is failed, which means your file is not available and you don't have corrupted data.
Any more questions?
We have some questions online, Boris.
Just 1 second. We're still finishing this question.
Got it. Okay.
So can you ask again? Sorry for that. Primary keys for what? This is not acting as a table. It's like acting as a Kafka topic. Iceberg has primary keys, but I don't know the context. Maybe I need to understand a little bit. For primary keys, for what kind of primary keys? Like SQL, Iceberg doesn't have the primary keys in that way.
Okay. My question is towards data parallelism. So with Kafka world, like I determined like the number of tasks, maybe in my Beam world could be like at least minimum the number of partition, Kafka partition, where like the data get partitioned between those many partitions, and then it get processed. So how does it work in Iceberg?
This is the beauty. That's why I was trying to emphasize that thing actually. For Iceberg, you are limited with your data processing worker. For Kafka, initially I also say in here, the rigid parallelism. You have to define in advance what is your partition count for that specific topic. Let's say that you have a 10 partition count for your specific topic. If your data processing job has 50 workers, or let's say that 47 workers, you cannot read from all of them. Basically you have to read only 10 of them, and the rest of the 37 is idle. But with Iceberg source, with streaming fashion, you can read all of them. And that's why in here I try to show that. Sorry, here. We do planning about your snapshot, and we decide that okay, these are my combined tasks, which based on the desired read size, and desired read size is coming from here, like read split target size. How much, how big you want to have a chunk, you can say 10 megabyte, let's say that. An Iceberg library is defined based on the files in file size, which combined scan task is happen. Let's say that you create 100 of the combined task. We distributed your 100 of the combined task by reshuffling across all of the available workers. And there is no case like Kafka case, you are reading just 10 workers, rest of them is idle. In this case, all of your workers are utilized and all of workers are independently reading without any scaling issue because you are using the blob storage rather than you try to scale your brokers.
Okay, let's do one more question from the room and then you'll go.
Okay, I got two questions. The first one is that, what about order guarantee? It looks like when you read those, you do all those like combination, you lose the order guarantee. And the second question is that, if I have multiple jobs consuming from the same table, then does that mean each of them is going to take snapshots independently and suddenly you have a lot of snapshots get generated?
For your first question, our ordering guarantees is level of the snapshot. Whatever you write in a single snapshot, you will get that data, and the second snapshot will get behind of the other data. But if you talk about the message, there is no ordering, yes, because we shuffle all of the data across the workers and we lose the ordering. And also, we don't know which order it's written because Iceberg doesn't support ordering also too. And per snapshot, you have ordering guarantee, and basically means that each chunk will come between, the behind in order. And for your second questions, snapshot is an Iceberg term, and basically it means that a set of the files and a view of the moment, for that table. And if you have a multiple consumers, they can easily consume independently, and it will not increase the snapshot. It is exact same the offset logic. You can think in that way. You have multiple consumers. Your Kafka message offset is always same, but your consumer may read, the different earlier or the latest offset. So,
let's say you have one application consuming and commits every 5 seconds. You have another one committing every 5 seconds. But if you have 10 of them, suddenly you're actually committing 10 snapshots per 5 seconds.
Yes, you are right. Yes. This is a streaming issue. That's why we try to solve that by doing the streaming auto compaction. This is not consumer, by the way. This is a producer, right? You produce your data to Iceberg table. If you are saying that as a consumer, you are not committing to offset or snapshot to Iceberg. You are committing your snapshot on your state backend. Yes. Yes, if you have a multiple producer, yes, this is the case, and you will create so many snapshots in the small amount of the time. For Iceberg optimistic locking, it has to be serialized. You cannot commit to offset, and this is a kind of limitation about for the latency. Why we cannot achieve the sub-second latency? Because blob storage, even though blob storage itself can achieve 400 milliseconds or kind of the latency, we are not able to commit the snapshot that frequently. This is the issue, and that's why when I positioned this presentation, it's a minute level, the latency required data pipelines. It's not second level or sub-second level latency.
Okay, let's go to questions online and to the next presenter. Efe?
So Tarun has a question with 2 parts. The first part of the question is, how does a pointer within snapshot maintained for exactly once record processing? And the second question is, what are downsides of using Iceberg over Kafka?
Can I take this second one first? It's easy.
Yeah.
First of all, Kafka is awesome for the sub-second latency requirement. So far, I don't think no one can beat it. And Iceberg streaming capabilities is, as mentioned, that the minute level. And beside of that latency, I see so many good things on the Iceberg side. and because it doesn't require the maintenance and the optimization. For Kafka side, I see so many maintenance, the DevOps job and observability. For the first question, snapshot exactly once is happened by, if they are asking about the producer side, Iceberg is implement optimistic locking, and optimistic locking means that basically you have a snapshot ID. When you try to write your snapshot, if the ID is changed, you have to retry until you reach a point like you are able to write your ID. And this provides exactly once while writing. And when you read it, it's totally independent from the Iceberg. It depends your streaming processing, and you can commit your snapshot on your state backend. And if you're streaming processing like data flow or Flink, it is, it can provide exactly once.
Great. Thanks, Talat. We have one more question, if I can also read that one.
Maybe, we a little bit tough on time. Let's do one more question. Okay, sure.
All right, then quickly, the question is, Mithun is asking, can Beam perform update operation on primary key of the raw Iceberg table, or is it append only?
For streaming read is append only. We are working on the merge on read and the copy on write kind of CDC related things. At least current state is append only.
Okay. Thank you.
All right. Thank you very much, Talat.
Thank you.
All right. Our next presenter is Nick. I'll stop sharing. Okay. Can you share? Meanwhile, I'll introduce Nick. Nick is, first of all, an alumni from LinkedIn, and he's an infrastructure tech lead at Metronome, where he focuses on reliability, scalability, and cloud cost optimization. Prior to Metronome, he helped scale Kafka and core infrastructure at Robinhood, and previously worked on backend platforms at Coursera and LinkedIn. Let's go ahead.
Hear me now? Yes. Awesome. Yeah, I love the talks tonight. I mean, it's really cool to see a talk about operations of massive Kafka clusters, and then talk about not using Kafka at all. I'm going to give more of a use case specific talk about how we use Kafka to solve a billing problem, which is typically a boring problem of infrastructure, but we're actually a usage-based billing company. So we actually do a lot of interesting stuff around streaming to compute bills and invoices. Cool. So this talk, we're going to be talking about, first of all, what is usage-based billing? Because I think a lot of you probably don't have a lot of background on that. We'll do a kind of high-level view of Metronome architecture, but focus on the streaming components. We use Kafka streams quite a bit internally. And we'll talk about some design patterns we use to make sure we can perform like maintenance and scaling on our stream processing topology with high availability. And finally, we'll go over some of the challenges we've had scaling our very stateful stream applications. So again, I'm Nick, tech lead for infrastructure at Metronome. Here I did my intro, but I will. I also wanted to shout out to, I was supposed to speak with Casey Kreitz, who's a founding engineer at Metronome. He's not able to make it tonight, but he put a lot of the blood, sweat, and tears into what actually built this system from the ground up. So I want to make sure I give a shout out to him because I'm kind of presenting a lot of his work here. Cool. So starting off, what is usage-based billing? If you haven't heard this term before, you've certainly seen it first or second hand because your cell phone bill, your electricity, your water are all metered usage. If you're using cloud providers, they're all probably billing you usage-based as well. Maybe you're paying for CPU hours or gigabytes stored per month or network egress. These are all examples of usage-based billing. And a lot of infra SaaS and AI companies have moved to this kind of model because it really aligns the value they're delivering with the usage that you're getting out of the product. It also lets you have much better visibility into your costs, so you can help control those costs. Metronome is one of these usage-based billing companies. We have a number of clients that you probably have heard of. A lot are, like I said, in the AI or infrastructure SaaS. Before we go on, just some quick nomenclature, because I'm going to be using these words a lot during the talk. Metronome is this provider of, billing provider, and we have clients that sign up to use our billing services for their customers. So Metronome's clients use Metronome to bill their customers. Cool. So how does the basic integration with Metronome work? Basically, we're going to be starting, our clients will be instrumenting their services to send events to us. And these are any events that could be generating billable usage. And for a lot of our clients, this means that every time like an API call is made or a resource is instantiated in their cloud, or for an AI company, it could be for whenever an inference is made, they're going to be sending us an event. And these events you can see in the bottom right corner there are just a basic JSON blob. They're going to have a client provided timestamp, a unique transaction ID per event. This is important for dedupe. They're going to have a customer ID, and then a bunch of properties that are describing things that are probably relevant to billing. Things like which cloud is this running on? Which region is it in? For an AI company, it might be like which model is being used or whatnot, because those are important for how you might price the usage. So all this data comes into Metronome. It goes through our usage aggregation pipeline. And this is going to aggregate the data at an hourly and a daily granularity. And then from that system will provide an interface for our invoice computation engine to query those usage aggregates and then apply pricing and packaging rules set up by our clients to actually rate the events and create an invoice that has an aggregated like line item on it with the actual price. This part of the system's like super configurable. It lets you model like any SaaS contract with constructs like discounts, tiered pricing, usage commits, prepaid credits, and a bunch of other things. And then these invoices are generated. And on top of that, we layer a few other services within our product, one of which is setting up real-time alerting on spend usage or things like that, as well as we have a way to enrich the invoice data and send it into our clients' data warehouses. And they use that for a number of purposes as well. So why is this a hard problem? With a typical billing system, you're really focused on correctness. That's obviously a very critical component. But with usage-based billing, you're introducing kind of this an observability pipeline on top of billing. So you have transactional observability requiring very low latency, as well as very high availability. On the correctness side, Metronome is a financial source of truth for our clients. They use it for billing, compliance, revenue operations. Some of our clients are public companies, so they're using this for quarterly earnings reports, of which if you get them wrong, you can be penalized or have investor lawsuits. So we want to make sure our data is very much correct. To make things a little bit even harder, these ingested events can come out of order, and we allow our customers to correct usage events up to 34 days in the past. So it's a very large window of which we have to accept these kind of backdated events. On the low latency angle, this is really to support a real-time alerting pipeline. So our clients use this for things like entitlement gating. So when one of their customers' credits run out, they're going to basically turn off access to that product they're using, hopefully in near real time. They also use it for fraud detection. It's very important that we're able to do this in sub-minute time, because for some of our larger clients like OpenAI, number of minutes of a large customer using their service could result in a very high cost to them. And secondly, our customers have come to expect even like our APIs and our dashboards to be in near real time. I do a lot of cost stuff, and I use AWS's Cost Explorer. It takes like a day or 2 days to refresh or get the most up-to-date data. With Metronome and a lot of these usage-based products, they've come to expect that to be basically instant. So it's kind of just an expectation now for us. Finally, like I said, our service has to be very high availability. We're not just like a batch job that runs once a month to send bills out. We have live APIs. Our clients will integrate with those APIs during their customers' onboarding flows. So they'll be sending a call to Metronome to set up that customer in our system for provisioning. Our clients also expect the data export to be very timely and fresh, because their C-suite members are using this every morning to look at their revenue data. Cool, and we do this at a pretty substantial scale, over 800 billion events ingested per month. Our P90 time to aggregate measurement is less than 15 seconds, and we calculate over 70 million invoices a day. Cool, so we'll talk a little bit about the architecture and how we do this. fundamentally, with like any kind of system like this, is taking some raw data in and computing aggregates. There's kind of two ways to do it. You can do pre-aggregation or post-aggregation, right? So for us, computing aggregates when the events come in at write time, it results in you'll have the invoices ready to serve. It's very low latency to pull those invoices, but if there's a correction, backdated usage, or a client changes their pricing and packaging, we have to kind of recompute the whole world. And for us, that's not ideal because that's our clients want to be able to rapidly iterate and make those changes and not wait for these massive like backfill jobs to finish. By contrast, on the other side, if you do everything at read time, it's going to result in a very slow query. You're pulling, for some customers, like millions or hundreds of millions of events together to build an invoice, and that's a very expensive query to run. So it's very high latency as well as very high cost. So at Metronome, we landed an approach kind of in the middle, where we have our customers define a set of what we call billable metrics that define how their usage events should be matched, filtered, and aggregated through our ingestion pipeline. And then we take those in and process through a Kafka Stream pipeline, and then we write them out to a number of storage systems, one of which is cold storage, just raw events into S3, an OLAP store, which is used for some operational things and a couple like niche product features, but most of our usage is in this hot sharded relational store that we store the most recent usage aggregates in. Cool. As I mentioned before, on top of that, once you have your aggregates, there's an interface of which our invoice compute layer. This is kind of the business logic of the company. Queries into that to compute the invoices using the pricing and packaging information defined by clients. And then again, on top of that sits kind of the product layer, which is like APIs and data export and alerting. Cool. So diving deeper into the alerts, into the ingestion pipeline. This is implemented as a somewhat, fairly complex Kafka Streams topology. This is a kind of actually a simplified view of it. If you look at it in our Confluent cloud and zoom out, they have a topology browser, and it's like just so many different processes there. It's kind of a little bit overwhelming. But the idea being, when data comes in, they're going to go through first a deduplicator. We need to really guarantee exactly what's processing in this pipeline, and we do use the EOS semantics very heavily in our implementation. Because if you don't do that, you're going to result in either underbilling or overbilling if you're double counting or dropping events. The events then flow into what's called a matcher. This is going to be taking in that billable metric configuration and deciding which events should be passed on, which match to customers, which are relevant. Then it goes into the aggregator process, which actually does the aggregation itself. This is also a very stateful processor. Finally, it's routed to the downstream data stores. Cool. Just as far as technology choice, this predates me, but it's about 5 years ago when these decisions were made. Kafka is obviously a very mature streaming platform, very large community. It's fortunate as a small startup, we did not want to have any hand in operations, unlike Netflix. I know they have a whole team running Kafka. We have just Casey. So we want to offload that to Confluent Cloud or another vendor. For Kafka streams, there's obviously different choices for stream processing systems, Flink, Spark streaming and whatnot. We like Kafka streams because it's embeddable. We can run it right on Kubernetes. But more importantly, it has probably the most mature exactly one semantics implementation of these stream processing libraries. And that was, as I mentioned, pretty critical to our use case. Cool. So to get a sense of why this EOS is so important to us, I'll talk a little bit about how clients integrate with us. They send their events to Metronome over just a typical REST API. As you might know, like with these kind of integrations, all kinds of bad things can happen. You can have timeouts on the server or client side. We can have 500 errors. We can send rate limiting responses back to them. And if clients just ignore these errors and they don't retry the events, they're going to basically be dropping events on the floor, resulting in loss of revenue for them. So we encourage our clients to, just persistently retry until they get a success response from us for a given event. We will only return a 200 success response if we have successfully written it to the top of the funnel topic, which is called the usage events buffer. We write that using the exactly once transactional producer, to make sure it just gets in there once. That said, this is a REST API. The clients don't have exactly once from the link from them to us. So they might accidentally resend a duplicate into our stream or send some backdated event as a duplicate. We want to be able to basically deduplicate those in our funnel. So to address this, there's a deduplicating processor in this stage, which is a very stateful processor that duplicates based on transaction ID. And at that point, it can write the events downstream via exactly one semantics to the next topic in the topology and guarantee that everything from there on out is going to be deduplicated correctly. And as I mentioned, this duplicator, it's a massive amount of state. It's a 34-day window, upwards of 100 billion events, in the store. I think our transaction IDs can be 128 or 256 bytes. So it's very large amount of state being stored here. And this has been kind of, has grown to become our nemesis over time. Thanks, ChatGPT. We've had to evolve the implementation of these state stores a number of times as our client usage has scaled. And these state stores are also annoying because they can become corrupted. When you have a rebalancing operation, Kafka streams may decide to rebuild them from the beginning of the change log. For us at our size, that could take over an hour to do, which is a very frustrating experience. It results in an SLO miss for our time to aggregate for our alerting product. Altogether bad. We'll dive into this a little bit later at the end of the talk about kind of how we scale this. But for the middle section here, I want to introduce a few of the stream processing design patterns that we use to help ensure that we can operate our pipeline with very high availability, supporting those correctness and low latency requirements from I was talking about earlier. So I'll share a few of these patterns. The first of which is like really simple one. If you guys do stream processing, you probably use this yourselves. This is called a shutoff valve. It's a really simple design pattern where it will allow you to perform safe and low impact pipeline maintenance and upgrades. So some changes like topic widening or making a riskier code change can result in, like I said, the state stores to be corrupted or whatnot. Other changes like maybe changing your Avro schema incompatibly will just flat out break your pipeline. So when we make changes like this, you don't want to be doing this as an online operation while everything's still flowing through. So what we do is we introduce this thing called a topic replicator buffer at the top of the funnel. This is a simple processor that just like copies events from the source topic into the destination topic. When we need to do maintenance on the rest of the subtopology, we'll simply just like scale down. This is a Kubernetes deployment. We'll scale down to 0 pods, such that there's nothing replicating, but we're still receiving events through our API tier into the top, that initial usage events buffer topic. So they're kind of being staged there while the rest of the events and data are being drained out of the rest of the pipeline. Once everything's drained out, we can safely do our maintenance. And then when everything's cool, we can scale back up that replicator buffer and start the flow of traffic again. This is really useful for us, like I said, because our clients really don't see any downtime per se at the API tier. They're still getting success responses from us, which is great. There is definitely, of course, the maintenance is incurring a stream processing downtime, but that's to be expected. The other trade-off here is, of course, it's slightly more expensive to run this extra hop in your stream processing topology. For us, it's not a terribly big deal because a lot of our cost comes downstream where we have a lot of amplification and fan out. So this is a pretty minor cost for us. A natural extension, other things you can do with this are introducing like feature flagging for dynamic routing into your pipeline. And so say like, if one of our clients is really blowing up or slamming us with volume, maybe we can reroute them to a different topic. So they're not like, head of line blocking for other clients that are trying to use our multi-tenant system. In other examples is like in our alerting pipeline, sometimes some of our customers, their invoice will become very expensive to compute. Maybe they had a change in the cardinality of their events coming in. And so it's like their line item just blew up and it's taking forever to process. We can just like black hole that customer and ignore them while our on-call does investigation and kind of fixes the problem. Cool. The next pattern is blue-green deployments. In this example, say we just want to widen a topic from 32 to 64 partitions. And so because of the way, Kafka is distributing data across the partitions, you can't really do this as an online operation with Kafka. In fact, Kafka streams will just I think throw an error if you try to change the partition count online because the data will just all shuffle around. So we need a safe way to roll this kind of change out. So instead we use this blue-green deployment pattern, which is very similar to the backend pattern that you may be familiar with. You kind of create a parallel processing pipeline. You name the current pipeline the blue variant, and it just keeps doing what it's been doing. It's reading off that smaller topic. And we insert another topic replicator buffer to copy the small topic data into this new larger topic. Then we deploy the green variant of the processor and just let a backfill run basically until the green processor state store is filled up, at which point then we can, at the very top of the funnel, pause all the inbound traffic again through our initial, our shutoff valve there, wait for all the traffic to drain out. At this point, we are certain that both the blue and the green processor have processed the exact same data. Their state stores are identical. At that point, we can just kind of point the upstream to the new topic and then turn back on the flow of data. I think that's there, resume. Yeah, cool. One more pattern for you guys, consistency checking. Question being like, how do you know your stream processing topology is producing the correct results? At our scale, we've encountered a number of novel bugs in not only our application code, but the underlying libraries. We've discovered edge case bugs in Kafka streams. We're one of the larger users of this with Kafka streams and EOS. This is not to say Kafka streams is a bad library. It's going to happen. Bugs will happen, and you can't just like hope is not a strategy. Just you hope they don't happen. They're going to happen. So we need a way to kind of verify that our online stream processor is doing the right thing. So we implement a consistency checker as a batch job running against our lakehouse. There's two data that is in this piece of data in this lakehouse. The first are just our raw events. On a previous slide, you saw we were shoving all the raw events into our lakehouse. We also take a daily snapshot of our hot storage system, these aggregate shards. So we're able to take a snapshot of that data into Iceberg format into our lakehouse as well. At this point, we can have a consistency checker job that basically takes all the raw events in Lakehouse plus our billable metric config and compute the aggregates on its own, and then compare those results to what we got from the snapshot from production. If there are inconsistencies, they are written to a queue. Now there's still some weird like timing issue around when we take the snapshot daily, but the raw events are coming in at a much more faster pace. A backdated event might creep in and throw off things that you'd see an inconsistency that's a false positive. So we do actually a separate recheck process on all the ones we found using two online systems. So we compare the aggregates in our hot storage system, the online one, against our OLAP, which is also in real time kind of processing the raw events. And we compare those. If they're still off, if it's still the value is inconsistent, we will page on call, probably a P1 incident, not a good time. And you probably have to go do database surgery or who knows what. But yeah, it's happened a few times for sure. Cool. So yeah, those are some patterns that got us pretty far in our scaling journey. But as I mentioned earlier, we continued hitting this kind of persistent issue with scaling our state stores, just operational issues. As we mentioned before, there are two state stores that are very large. We have a lot of state stores, but these are the two largest ones for the deduplicator and the aggregator. So as our customers' usage grew, as I mentioned, we kept hitting kind of frequent state restores, corruptions. This would be due to like a consumer group rebalance, maybe a Kubernetes node crash, maybe a specific Kafka Streams processor instance crashed or got into a bad state. Oftentimes that will result in rebuilding from the beginning of the changelog, taking up to over an hour at times, which really impacts our SLOs. And this is particularly painful for our on-call engineers because there's really operationally nothing they can do but just wait and just look at the logs. I mean, this is this screenshot or the profile picture of Casey when he was on call in this era, and his Slack status was just restoring ... because that's the log message you see printed out incessantly when a Kafka Streams app is restoring, and it shows the percentage too. But yeah, you sit there and watch that, and at 2 a.m. it's not a good time. So yeah, we realized we're kind of fundamentally pushing the limits of what Kafka Streams default architecture could do for us, and we needed like a new approach to scale our state. By default, Kafka Streams, that has like in-memory stores. By default, it uses RocksDB as a local state store. And what this involves is like every Kafka Streams application, every instance has its own RocksDB kind of basically partition of what's effectively a distributed database of RocksDB databases. And these are, as you know, distributed databases are very hard to operate. In fact, Kafka Streams itself, a number of the bugs in the library historically have come from state stores, specifically in situations where they're rebalancing, especially when EOS is involved. These are just very complicated implementations to manage, and there's so many different race conditions and weird things that happen in the wild that they just break quite often. To solve this, Metronome actually partnered with a startup named Responsive. They are kind of an offshoot, a few, they're ex-Confluent employees. They kind of worked on Kafka transactions and other sorts of very nuanced implementation details within Kafka. And they helped us kind of move our local RocksDB storage to a remote distributed database. The challenge here is that, a remote state stores just out of the box do not work with EOS. Because Kafka Streams expects that they're able to like wipe all of the RocksDB local state out, and now there's this remote database they really don't know how to interface with. So the implementation is actually super interesting, and I just watched the talk on it today. If you want, I put a QR code link to it there. But the responsive team gets into like really nitty-gritty details about how they implemented that a remote state store. We happen to use ScyllaDB with them. And they involve things like fencing and tombstones and a kind of unique database schema to handle that. They actually intercept when there's a crash recovery in Kafka Streams. They actually intercept the offset. How Kafka Streams picks the offset, they actually provide their own from the distributed database, the remote database. Sorry. So yeah, very interesting problem. Very pretty challenging. There's also challenges of like moving from what was first initially a very low latency local disk to now a remote database in the cloud. They kind of helped us kind of solve all of these things, and it works really well. The second thing they kind of help with is pulling out a control plane for us for Kafka Streams. They provide an operator as well as an auto-scaling controller. It takes in a bunch of different metrics, either mostly from Kafka Streams or from your application, and just makes pretty smart auto-scaling decisions for your less stateful applications, and that's really helped us be more responsive, I guess. So it results of that, now we can handle pretty massive traffic spikes. This is a pretty old screenshot, but when we have a spike come in, the autoscaler will kick in and scale up our stream processors. In our remote database, we're storing now, it says 8 terabytes here, but it's actually upwards of 20 terabytes of data of transaction IDs in that database. And where it would have taken hours to rebuild RocksDB, now it's basically our applications come back online in minutes after a rebalancing event. So it's just far fewer incidents, much happier on call as a result. Looking ahead, this ScyllaDB works really well, but it has some disadvantages. It's using local SSDs, which are very expensive. Also, these databases are kind of a little bit heavyweight for the simple kind of timestamp key value store that we need. So one thing we're looking at in the future, we haven't done it yet, but with responsive is to replace ScyllaDB with a new kind of storage layer. They're calling RS3, I think. I don't remember the exact name, honestly. But it's basically based on SlateDB. Anybody heard of SlateDB? No? Maybe one person, nice. So this is basically like, it's LSM trees, like stored in object storage in the cloud. So in S3, which is pretty powerful. So now your storage is elastic. You get bottomless storage, very strong durability. The cost is really low. So yeah, just kind of following that trend of like a lot of storage moving to object storage, as the previous speaker was mentioning, which is continuing that trend. So yeah, also this system will be easier to debug because your data is all in S3. You can hook up Spark jobs or Presto to query it or what have you. So yeah, that's basically what I have for you guys. Yeah, we can open up to questions. All right, which one? Go ahead. I suppose. I mean, you saw the schema for the event. I suppose that was the structure of the events we're processing. It's yeah, exactly. And I mean, the structure through the streams pipeline is Avro. In the data lake, it's into Iceberg format. Does that answer your question? Yeah, I don't think our data is pretty strongly typed. I mean, actually, sorry, we do have a JSON column. Sorry for the properties. You're right. So that is very much semi-structured. Yeah. Yep. Yes.
For your blue-green deployment, you mentioned you're gonna run a copy of your pipeline on, let's say, a topic with more partitions, right?
Yeah.
But some of those processors could also be stateful, and they're aggregating over, let's say, 60 days of data. So are you processing all of that data in your second deployment, waiting for it to catch up before you can do that shut off and migrate over? And how costly is that?
It's expensive. This pipeline is pretty expensive for us, for sure. I mean, for that, I mean, it's actually not too bad. I mean, like I said, a full restore of our largest state stores takes like a number of hours, basically. So maybe a day at most, and you can really just scale up that processor to speed it up. So it is costly. This doesn't happen that often. These topic widening events are like every like 6 months to a year, probably. We just at one point we just sized them up like huge and just said, screw it, 256 partitions and be done, because we're kind of tired of incrementally bumping them. But yeah, there is some cost.
Question here, sorry. So you showed you do the error detection or error check on the like a daily basis.
Yeah.
Do you also do any anomaly detection, or do you let the companies deal with any anomalies?
Anomaly detection.
Yeah.
Not that I know of. No, this is. I mean, I'm sure it'd be helpful in some places, but for us, it's more about like we're just making sure that our numbers are exactly correct.
And is there a negative billing that you can do, or to correct past errors?
You can send negative usage events. In fact, I've used that a few times to help some of our clients. Yeah.
Can you give a little bit more detail on the causes for the need for state store rebuilding for things that were causing other? How much of it was infrastructure changes, to your point, topic changes? How much of it was you're upgrading the streaming app? How much of it is, oh shoot, Kubernetes failed, or the streaming app itself had a bug, or whatever? I just want to get a sense of what your Kafka Streams usage pain points were.
Yeah, totally. A lot of times I'd get paged at 2 a.m. and it'd be completely random. Just like some rebalancing loops happening. And you're like, why? I don't know. And you kind of, you might cause it, you might not. A lot of times it's kind of like just random behavior. Sometimes it was, like a legitimate fail, like out of memory, a certain pod instance crashed. More rarely, of course, that whole Kubernetes node would go down. That's pretty rare for us. But those are the most common things, just like random rebalancings happening for some reason. Maybe one of the processors was lagging behind by too far for some reason. I don't know. Yeah, I think 50% of these, like, we actually didn't like root cause, because there's like, it's pretty hard to debug some of these things. There's a lot of machinery running in these Kafka streams applications.
I was wondering about for deduplication, the format of like the transaction ID, because I would imagine there might be instances where two events might have the same transaction ID, but then payload might be slightly different. So in those cases, would they be compared byte to byte, or would one just automatically be eliminated?
Yeah, good question. It's client specified ID. So I mean, on our side, it's namespaced by the client. So we don't have like IDs across clients like that would, that's a part of the key for us. But yeah, if they happen to provide the exact same transaction ID for two different events, that's their problem. It basically gets deduplicated.
Yeah, thank you for the presentation. I just wonder, what do you use for billing your clients? Do you use Metronome to bill your clients?
We do. In fact, that was like my first project at Metronome, actually, because there's a ongoing, I think for like years ahead, we said, we really should be using our own system to dog food and like bill our own clients. And I think it was a project kept getting handed off between engineers and no one ever finished it. And even I didn't exactly finish it, but I got really close. And then another engineer really finished it. They pay what? We have our own usage-based billing on Metronome. I mean, it's basically that one of the main components is the events sent. So if you send us a lot of events, you're charging per 1,000 events. We charge per data rows exported. We charge per a bunch of different kind of product features.
Detail of the billings, maybe like if they have too many attributes for the billings, like too many breakdown of the billings, maybe
that's something we're introducing right now. In fact, like we didn't have that as part of our pricing model, but we're adding basically cardinality as a factor, or aggregates. Because yes, if you send us ridiculously high cardinality data, it really blows up our pipeline. We don't like that. I mean, we don't mind. We'll scale it, but like we want you to pay for it. There should be some penalty. Yeah.
Did Slate DB solve your state backend restoring issue?
Sorry, did we run into issues? Sorry.
You mentioned about the restore state backend for the RuxDB, and you moved to Slate DB, right?
No, that's the future work. We moved to Scylla DB.
I see.
Slate DB would be the next thing.
Maybe you can try, this is just suggestion. You can try Clip DB. It's a feature for RuxDB. It's not a separate DB. It's a patch, for a while the RuxDB is provide. The restoration waiting is happen because SSD files has to be merged and, to get in the one DB. clipdb is just read the offset of the files rather than reading the whole files.
You said clipdb?
Yes.
Okay, I'll check it out.
One more question from the room and then a question from online.
Yeah, thanks for talk. A question is about the your code storage and hot storage. You mentioned that the data for users probably like 30-day range for they to check their correctness of data. So do you mean the hot storage keep the data for 30 days, and the code, like how long do you store the data, and why do you need the code storage?
Yes, there's different retentions at play. I mean, for the stateful stream applications, that's some of them are 34-day windows to retain data, say in our change logs in Kafka. For data we push into like our lakehouse, it's stored basically forever. We have events since 2021 or whatever in there. So yeah, we just keep that mostly forever. We don't have many retention policies there.
Okay, Efet, do we have any online question?
No questions online. Actually, no, wait. There's one question online. V. Narayanan asks, do you allow backdating of the usages? How long one can backdate usages, and how does it handle out of order data in those situations?
Yeah, it's a good question. So we do allow people to send events back as many as 34 days in the past. It's going to come in if it's not a duplicate, of course. It's going to get into our system, and our aggregator, since it has a state store and a tumbling window set up over 34 days, it'll be updating that bucket from however many days ago, then persisting that to our database. So yeah, all those windows are open for 34 days. And so that's kind of just a feature of Kafka Streams. And the trade-off being it's very expensive to keep all the state around in memory as well as in our state stores.
But then you have to rerun invoicing on top.
Well, at that point, I mean, the aggregates are computed, like when they send it back to the events, the aggregates get updated right then and there. And so the invoices are now up to date. Yeah, at that point, because we compute the invoices on read live.
All right. Thank you very much, Nick.
Yes.
Great talk. And thank you everybody for coming. The recording will, when the recording is available, we'll publish it on a Meetup page. Feel free to grab some food on the way out if you want. And thank you again for coming.